Hi, everyone. Next speaker is Chen, and he is going to talk about stochastic PDEs and well closeness of them. Okay, so solutions of stochastic PDEs. First, let's start with some background. So this is the setting, and it describes both stochastic heat equation and wave equation. So those are just the cases, special cases of this equation. And this is a Caputo fractional differential operator of order beta. So it's defined this way, and this is the ceiling of beta. It's going to be the usual derivative in beta order. If beta is equal to the ceiling, it's true. And then it's equals to this form if it is not equal to the ceiling. And this is just the usual gamma function. They also have this I of the function, so it's a Riemann-Liouville integral of order alpha. So it's defined this way, and they define it going to the A to 0 from the right. So A, and then 1 over gamma alpha. And then you have this, so of function f. So you have like rho in their paper, and it's defined in this integral form. Another thing that we see is, so like in here is not, but some other papers, such as this one, they consider the fractional Laplacian. And that one is defined, so like just if you just have alpha, it's defined this way, u over y. So d is the dimension, so we're talking about RD, and then alpha is what you start with, so order alpha. And then another usual fractional Laplacian, it will be alpha over 2. So we're talking about alpha being like in here between 0 and 2, and in here it's between 0 and 1. And then it's given the similar form. So again, D is the dimension that we're talking about. So that's the Laplacian, fractional Laplacian, and this is the way to figure out, like intuitively understand what it means. And then another term that they use is uniqueness in sense of versions. That just means different modifications or versions. So modification just means probability of x equals to y is equal to 1. And they are indistinguishable. So for some set, they're not equal to 0. They're not equal to each other. So that's uniqueness in sense of versions. So different modifications are indistinguishable. And this kind of sense is used when we're talking about random fields. So their solutions are random fields. So that's why we need this kind of uniqueness. So in his talk, he talks about these equations. So he has written with collaborators many papers where he considers this kind of equation, which describes heat and wave equations, stochastic heat and wave. So like for this one, for instance, if you said D equals to 1 and beta equals to 1, so capital fractional operator, differential operator, so beta equals to 1, and then so this is the way that we defined over here. So this is the operator. And if beta equals to 2, then we have wave equation. Everything else is the same. So Li Chen, Yao Denzong, Hu, David Nallard, they consider this equation with I given in last slide and prove well presence of solutions. And they also consider the uniqueness in versions. So this well-posedness is actually uniqueness in sense of versions that we defined. And they do moments, they prove moments. So second moment, upper bound and lower bound, and then weak intermediacy. So the limb sup and then limb if 1/t log of expectation of the moment, and find lower bound and upper bound. For upper bound, they can do p greater than 2 for even numbers of p, and then for lower bound is all p greater than or equal to 2. In his paper, he considers this equation, so it's very similar. And again, we can have a stochastic heat and wave equation. So in here, I replace D with this notation to be consistent with others, but it's the same. This is just a capital fractional differential function. So it's the same. They just use this notation in their paper here. And then well-posedness again they consider, and this is well-posedness in the sense of versions. And then they do moments, very similar to last paper. It's just a small variation in their equation. So I think it's like I is different. I, and then also like in here is not fractional Laplace. Here is fractional Laplace here. So the setting is very similar, and they prove well-posedness against sense of versions, moments, and weak intermittency. And in here, they consider slow diffusion, which is better in 0, 1, and fast diffusion, better in 1, 2. And then they cannot, they couldn't prove lower bound for fast diffusion, which is better in 1, 2. Another paper again does the fractional Laplacian and capital differential operator, so very similar. And they again do well-posedness, existence, uniqueness. In here, they don't do versions. I think it's because they don't have random fields, or maybe they just don't say it. And then moments they prove. And one more paper is this one that feels similar to this one. It's just over here is different. So maybe the boundary conditions are also different. But the structure is very similar. So these papers I will share on the website so that you can see them. And they can prove well-posedness, again, in sense of versions, and then moments. So the goal of this talk is to show that, let's see, I have that open, maybe I didn't. To show that these are, let me think. Yeah, so let me open it up. So you have the interpolated equation that we showed, and then we are trying to link the stochastic heat equation and stochastic wave equation, and try to get information for both of them and kind of bridge the gap. So in their talk, they're trying to do that and explore this equation, which characterizes both heat and wave equation. All right. Okay.